This is the year 2022 and you can notice that most of the gadgets around you are powered by solar. Well, the world is improving newer solar technology that is going to be more efficient than ever. Yes, we'll be seeing in the coming years with the humongous application of the new Solar 3.0 technology. So what exactly is a Solar 3.0? And how it is different from the previous generations of solar technologies? And where will all be applied on? Let's see. In today's episode, we will be looking into how the new Solar 3.0 technology could change everything. Hey folks, welcome back and you're watching FutureTech Eden. What are you guys waiting for? Like, share and subscribe. The future of solar energy focuses solely on two well-recognized solar energy conversion technology groups. In their present and likely future forms, photovoltaics and concentrated solar electricity are often known as solar thermal. Because energy supply facilities generally have a lifespan of many decades, technology in these categories will dominate solar power generating between now and 2050. And when looking at photovoltaics, we can see a huge potential as it is more convenient. Renewable energy is much desired in order to achieve self-sufficiency in the methods of producing power. We have common sources like solar, but it has certain drawbacks. They necessitate investment not just in technology but also in land in order to build solar farms that generate power for consumption. Another concern is that they lack the energy density to generate enough electricity to fulfill the huge needs of industry. Another complication is the materials utilized to construct solar cells. They are unable to produce power with optimal efficiency. These difficulties can be solved using breakthrough technologies that improve material efficiency. Yes, one approach is to employ perovskites, a hybrid organic and inorganic material. Didn't get it? Let us explain. First of all, solar cells are classified into two categories. These cells absorb photons from the sun, generating electricity's electrochemical processes. We have crystalline silicon-based wafer cells used in many solar panels. Thin film cells, which can utilize perovskites, are another form. Thin film cells are constructed from layers of photovoltaic materials placed in a glass, metal, or plastic substrate. These substrates are more adaptable and versatile materials. Perovskite is mostly composed of methylammonium, lead halides, and all inorganic cesium, lead halides. Quite a mouthful, huh? These are chosen because they have the benefit of being less expensive and easier to manufacture than silicon-based solar cells. These cells also increase the conversion of sunlight to power by up to 25% in 2021. They produce electricity more efficiently rather than wasting energy in the form of heat. The ABX structure is seen in perovskite materials. This comprises two positively charged ions A and B known as cations and a negatively charged ion known as X or anion. Perovskite materials are defined as materials with same crystal structure as CaTiO3. By the way, do you know why perovskite is called so? The material was named after scientist Lev Perovsky, who discovered the minerals that have these properties, and that's what we're about to employ now. Okay, as we're speaking, scientists realized that by using the same layout, they may create their own material with the same or comparable qualities. Lead iodide and organic salts are examples of metal halide salts that can be utilized to make. They are then rolled into thin films that will be utilized as semiconductors. What exactly are the differences between these new sets of panels and the older ones? Or you could basically call them advantages. According to the Shockley-Queisser limit, solar cells in a standard panel are expected to be 30% efficient. If you're unsure what this phrase means, it's the theoretical limit of the solar cell with a single p-n junction. In practice, solar panels that employ silicon semiconductor solar cells achieve only 20 to 25% efficiency. Thin film cells based on perovskites can improve efficiency and provide greater power generation for energy. Perovskites may allow multiple p-n junctions, often known as tandems, that absorb distinct wavelengths of visible light by using a broader band gap. These are the many wavelengths emitted by sunlight. These tandems can also be used in conjunction with silicon cells to generate extra power. Got it? As a result, perovskites can theoretically enhance efficiency by up to 45%. What precisely do these benefits imply? The increase in efficiency can be ascribed to further advancements in device layers and design, perovskite growth processes, and the use of mixed halide perovskite with increased electrical characteristics. Not only that, but perovskites are more numerous than silicon. Therefore, the supply can lower material costs because it is not scarce. These occur naturally and may be found all around the world. It is also simpler to manufacture, needing less energy to process than silicon semiconductors. This occurs throughout the solar cell manufacturing process. Silicon crystallizes at temperatures of 1400 degrees Celsius or higher, whereas perovskites can crystallize at temperatures of more than 100 degrees Celsius. Besides, it is more versatile in terms of form factor since it can be manufactured into thin film cells. This makes it excellent for creating more adaptable goods. It enables the installation of solar arrays on items that would typically be incapable of supporting stiff silicon-type cells, for instance, in windows and even on automobiles. That's something, right? Making it seem easy when spoken about, but it really isn't. Yes, perovskite solar cells pose some challenges. The issue is, why are perovskites not more widely used in the market, given the benefits they may bring? This is owing to the difficulties in manufacturing them. The following difficulties confront perovskite solar cells: toxicity of compounds such as lead, material instability once introduced in manufacturing, longevity, and methods to make them live longer are all examples. So in essence, the technology is still in its early phases with no demonstrated track record. The use of lead in perovskite solar cells is environmentally hazardous. Lead is a poisonous chemical and leakage from cells can endanger human health. It can also harm the environment by contaminating neighboring vegetation and making its way into water systems and soil. Engineers must identify other perovskites to replace lead or devise a method to successfully prevent any lead impurities from seeping out. The materials are also less stable after the cell is formed. They must pass stringent testing before they can be called production level quality. The issue is that even if these cells can initially pass the test, they do not behave as predicted in the actual world. They can disintegrate at temperatures over 90 degrees Celsius. This can cause hysteresis in materials, causing their electrical characteristics to change. Perovskite's lifespan is also under doubt. Silicon cell solar panels have a lifespan of 20 to 25 years. As a result, manufacturers provide consumers with a 25-year warranty on solar panels. Perovskites have the disadvantage of being sensitive to moisture, oxygen, and heat. As a result, they require additional shelter from the weather in order to live longer. Unfortunately, this may raise production costs. It will become clear whether it can be a viable product over time. Silicon solar cells have been in use for decades. It has been tried and tested, however, it does not produce as much electricity due to inefficiencies. They are nevertheless quite stable and can be mass-produced. We recently talked about the stability of these perovskite solar cells. This is something more concerning than other aspects of the panel. Of course, you would want to build panels with it, so durability is desired. Perovskite solar cells have been shown competitive efficiencies with the potential for improved performance, but their stability is relatively restricted when compared to leading PV technologies. They do not withstand moisture, oxygen, lengthy durations of light, or high heat. Researchers are exploring deterioration in both the perovskite materials and the contact layers in order to improve stability. Improved cell endurance is critical for the commercialization of perovskite solar devices. Despite the substantial understanding of perovskite solar cells' stability and deterioration, current operating lifetimes are not economically feasible. Although mobile markets may accept a shorter operating life, stability during shortage prior to use is a critical performance criterion for this sector. Regardless of any benefits, systems that cannot function for more than 2 decades are unlikely to be feasible for widespread solar power generation. Early perovskite devices deteriorate quickly. Until recently, most perovskite devices would deteriorate to non-functional stages in minutes or hours. Multiple organizations have now exhibited operational lives for several months. SETO is aiming for an operating lifetime of at least 20 years, preferably more than 30 years, for commercially grid level power production. The perovskite research community is mainly focused on operational lifespan and is examining a variety of ways to better understand and enhance intrinsic and extrinsic stability and deterioration. This is something very much in need if we hope to use these panel techs in the coming years. Improved surface passivation of absorber layers, alternative materials, and formulations for absorber layers, charge transport layers, and electrodes, and advanced encapsulation materials and approaches that mitigate degradation sources during fabrication and operation are among the efforts being made. One challenge in evaluating deterioration in perovskites is creating uniform testing and validation techniques. Performance findings from various test settings such as encapsulation techniques, air composition, lighting, electrical bias, and other characteristics are regularly reported by research organizations. While such a wide range of testing settings might give significant insights and data, the absence of uniformity makes it impossible to directly compare results and anticipate field performance from test results. This impacts the whole perovskite research and development community regardless of the study field, material set, or technique to improve stability. Let's keep all of these technical parts aside and let's look into how much we could manufacture. To produce perovskite solar cells, perovskite manufacturing must be scaled up. Making the techniques scalable and reproducible might boost production and allow perovskite PV modules to reach, if not surpass, the office's levelized cost of energy objectives. The cells are thin film devices made up of layers of materials that have been printed, coated with liquid inks, or vacuum deposited. It is difficult to produce homogeneous high-performance perovskite material on a wide scale, and there is a significant variation in performance between small area cell efficiency and large area module performance. The future of perovskite production will be dependent on overcoming this difficulty, which is still an active topic of study in the PV field. Several techniques have been explored to create lab-scale perovskite devices. Many of these processes are difficult to scale, however, substantial attempts are being made to apply massively efficient methods to perovskite production. There are two basic types of manufacturing lines for thin film technology. It is done sheet by sheet and roll by roll. Device layers are deposited on a rigid substrate, which commonly serves as the front surface of the finished solar module via the sheet-to-sheet process. This method is widely employed in the cadmium telluride thin film sector. Device layers are deposited on a flexible substrate and roll to roll, which may subsequently be employed as either an interior or outside section of the final module. Researchers have attempted this strategy for different PV technologies, but it has not gained substantial commercial momentum due to challenges to achieving high solar conversion efficiency that is dependent on the production method. Nevertheless, it is frequently utilized in the manufacture of photographic and chemical film and paper goods such as newspapers. Because of the stability of these production methods, perovskites have the potential to permit quicker capacity increases than silicon photovoltaics. Because the processes under discussion are well established in the film and display industries, the expertise and supply chains around the tools and components may be easily exploited to further cut costs. An obstacle to the vast commercialization of the panels is the possible environmental effect of the lead-based perovskite absorber. As a result, alternative materials are being investigated in order to assess, reduce, mitigate, and maybe eliminate toxicity and environmental issues. Now, let's see the targets which have been set for the PV panels. SCTO analyzes developments in research and development and manufacturing communities and works with possible interested companies, investors, financiers, and end users to develop benchmarks and objectives for the commercial deployment of perovskite photovoltaics in the bulk power generating industry. These benchmarks and goals will most likely alter as we know what will enable the production and deployment of gigawatt-scale perovskite photovoltaics. Various materials, device architectures, and manufacturing procedures are being investigated, although it is unclear which approach is the most promising. Single-junction perovskite cells and modules will have different aims than hybrid perovskite tandems and all perovskite tandems. The following are some broad early-stage aims for perovskite PV commercialization. Later-stage objectives are being developed and will be released in the near future. As perovskite PV becomes more commercially viable, a balance must be struck between exhibiting high-power conversion efficiency and stability, leveraging scalable manufacturing techniques, and scaling from single cells to multi-cell modules with greater active surfaces. To drive perovskite PV technology towards commercial viability, power conversion efficiency objectives of 18% to 25% are required in the early phases. After 1,000 hours of accelerated testing, these modules should be able to exhibit operational stability, keeping 80 to 95% of their initial output. These values will need to be improved more in the future to approximate the planned decadal operational lifespan. Meanwhile, these criteria serve as a good indicator to assist the perovskite community in increasing dependability. Once better energy density and more efficient solar cells are created, the world will be less reliant on carbon. Carbon emissions may continue to fall as solar energy becomes more widely used in the next decades. Solar cells made with perovskite will produce more power. It can be used for new sorts of surfaces since it can employ more flexible substrates. Consider its uses in delivering electricity to homes and buildings, automobiles, trains, trucks, and even airplanes. This is a positive viewpoint for solar energy's possible utilization. The usage of numerous connections and novel materials in the manufacture of solar cells is predicted to improve. So as we come to the end of today's episode, what do you think of the new Solar 3.0 tech? Is it going to take all over the world just like its previous generation did? Moreover, what are your thoughts on today's episode? Anyways, please share your thoughts on today's video in the comments area below. That's all we've got for today. Make sure to subscribe to our channel if you want to see more videos like this one. While you're at it, enable post alerts so you don't miss any of our future uploads. If you enjoyed today's video, please give it a like. We hope you had a good time watching this video. We'll see each other again at the next one.